compartments with a rocket engine at its base. Each solid fuel booster arrives on its table in an upright position and preloaded with propellant. The upper stage, that will on this mission deliver 4 Galileo navigation satellites to their target orbits, is fitted. The satellites, clustered about a central dispenser, are then attached to the upper stage before the fairing that protects them during the trip up through the atmosphere is lowered into place. The Ariane, on top of the launch platform, begins its journey at a snail's pace. The Ariane 5 is operated by Arianespace, who have launched more than half the commercial satellites in operation today. Russia's heavy-lift Proton launcher started its life in 1965. It was originally designed to carry a 100-megaton thermonuclear weapon to targets in the US. It was never deployed as a missile, instead evolving into a successful heavy launcher. It delivered several modules to the International Space Station, and one of its recent high-profile successes was the launch of the first ExoMars probe. But the Proton has not been without its problems. Developed during the Soviet era, its manufacturer Krunichev was reliant on the Ukraine for key components. And when launched from Baikonur, the Kazakh government was not keen on the extremely toxic hypergolic fuel it used. There are claims that acid rain falls after some launches, and that parts of Russia and Kazakhstan are being poisoned by the unsymmetrical dimethyl hydrazine that powers the Proton. At Baikonur in July 2013, a Proton-M was set to launch 3 Russian GLONASS navigation satellites. An investigation package had been installed upside down. It was not the only recent Proton failure, and questions about quality control were being asked. Years, it will be phased out. Startup company Spacelab is poised for its first commercial launch. Their rocket, called the Electron, can deliver light satellites that completely undercut the rest of the market. The launcher makes extensive use of carbon fiber in the construction of the tanks, and Spacelab has developed an engine with a radically new fuel cycle. Named after physicist Ernest Rutherford, the engine is largely constructed with 3D printing techniques. The liquid oxygen RP-1 fueled unit uses brushless electric motors to operate its turbo pumps instead of pre-burning fuel for the same purpose. The batteries powering the process add weight, but they save on fuel and give engineers finer control when throttling the engine. The launch site on New Zealand's North Island Mahia Peninsula is perfect for the busy schedule that Rocket Lab envisions. For a new area of the launch market. The space industry is at a turning point. The launch system is about to fly. With it, the new Orion spacecraft, A collaboration between NASA and ESA will target the Moon. A landing is scheduled for 2024. As far as the United States is concerned, low Earth orbit is now the province of corporations, with Boeing and SpaceX competing to break Russia's stranglehold on manned trips to the International Space Station. New technology is cutting costs and increasing launch frequency, with complex satellites being so small they can be deployed in new ways. Several companies are working towards space tourism. Virgin Galactic says its promised trips beyond the atmosphere should start happening soon. Since the retirement of the shuttle in 2011, space science has shifted focus to research carried out on the International Space Station and to robotic missions in deep space. During this period, all manned flights have been to and from the ISS, with the only viable spacecraft being the Russian Soyuz. This has cost both NASA and ESA billions in launch fees. Russia, Europe and Japan, major partners in the ISS, developed their own cargo craft to resupply the space station. But NASA tendered for private companies to take on these responsibilities. Rising star in the launch business, SpaceX, was contracted to develop a cargo craft that would launch on its Falcon 9 rocket.
3, 2, 1, 0. Launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
A second aerospace business, Orbital Sciences Corporation, now Orbital ATK, signed a contract for similar hardware and services. NASA is developing its own launch system and the Orion spacecraft, but it's designed for missions far more ambitious than resupplying the ISS. America's activity in low Earth orbit is being reallocated to the commercial sector, and NASA is helping with technology transfers. Agency administrators want two completely different systems, giving the space agency what they call dissimilar redundancy. When the Space Shuttle twice suffered catastrophic failures, NASA was stuck on the ground for years while exhaustive investigations were made. The redundancy approach will prevent this paralysis. In 2014, NASA signed contracts with Boeing and SpaceX to develop and test human-rated spacecraft to ferry astronauts to and from the International Space Station. It was a continuation of the dissimilar redundancy approach. The space agency has set performance criteria for the new craft and crew training, but is taking a hands-off approach regarding how the companies meet the requirements. Boeing's spacecraft is called the Starliner. It has space for 7 astronauts and will be capable of being used 10 times. NASA requires any human-rated spacecraft to meet higher standards of safety and reliability than a cargo craft, and new capsules must demonstrate, via a series of test flights, that they meet certification.
5, 4.
One crucial part of the new spacecraft is the launch escape system. It's the equivalent of a fighter pilot's ejector seat.
Picture on.
Both Boeing and SpaceX have opted for a new method of capsule-mounted rockets to push the craft clear in an emergency. in contrast to the more traditional escape tower above the agency's new Orion spacecraft. The trial of Boeing's escape system worked well, with the exception that only 2 of the 3 parachutes deployed, but the problem is understood. The Starliner could continue to the next uncrewed launch to orbit. One of the novel features of Boeing's capsule is its ability to return to dry land, like Russia's Soyuz craft. Airbags, stowed behind the heat shield, inflate prior to landing. Without the need to deploy ships for an ocean recovery, there will be considerable savings. Though the capsule can fly on the Delta IV, the Falcon 9, and the yet-to-be-flown Vulcan, initial testing of the spacecraft has been with the Atlas V launcher. The Atlas ground support infrastructure has been modified to accommodate the Starliner with the addition of a crew access arm. The Starliner made its first unmanned test flight in December 2019. Its destination was the ISS. The launch was perfect, and 4.5 minutes after liftoff, the first stage separated. Next, the boost protect covers and the aeroskirt were jettisoned, and the Centaur upper stage burned for a further 7 minutes, following the course parameters perfectly. After separation, the capsule was in a suborbital trajectory, selected because it allowed a safe path back to the ground in case of a malfunction during the boost phase. To achieve the correct orbit, the craft was required to fire its 4 attitude and orbital maneuvering thrusters 31 minutes after liftoff. However, the Starliner's sequence clock was incorrect, and the orbit insertion burn did not happen. Ground control was able to salvage parts of the mission, but the craft was not able to reach the International Space Station. This setback will delay the Starliner's first mission carrying astronauts. SpaceX's Crew Dragon capsule is a refinement of the cargo craft that first flew in 2010. From the beginning, the Dragon capsule has had a heat shield, enabling it to return safely to the ground. No other ISS cargo craft has had this ability. In addition, the Dragon also has a window. This should have been a clue to SpaceX's long-term plans for the craft. In 2014, after the contract for a human-rated craft was signed, SpaceX began work on the Dragon 2. Like its Boeing equivalent, the Dragon 2 sits above a service module that can carry unpressurized cargo and includes a heat exchange unit and a coating of solar cells that does away with the moving parts involved in extendable solar wings. The Dragon 2 can accommodate 7 astronauts, though NASA has said it will generally only send 4 people at a time. Control interface is via a touchscreen. Cape Canaveral's Launch Complex 39A has been equipped with a crew access arm, and in March 2019, in a flight known as Demo 1, the unmanned craft made its first spaceflight. The Dragon carried a dummy astronaut, wired with sensors to monitor G-forces, and a small delivery of equipment for the ISS. The launch and the phasing maneuvers to align its orbit with the ISS were all correctly executed. The automated docking procedure went smoothly, and the Dragon stayed connected to the space station for 5 days. Decoupling from the ISS went as expected, and observers on the ground were delighted with the capsule's behavior. Throughout the mission, every aspect of the Dragon 2's performance was monitored. The craft's return to Earth was faultless, and the recovered capsule would be reused for the one remaining uncrewed flight test. SpaceX planned to use new capsules for manned flights and then recycle the craft for cargo use. Confident planners at SpaceX and NASA were looking toward the first crewed flight. The final certification test was an in-flight simulation of a booster failure that would monitor the Dragon's launch escape system. But before that, the craft's Super Draco engines, used in mission aborts, needed retesting. This was considered routine and had been carried out many times. A leaked video revealed an explosion that had destroyed the capsule. The problem was not engine failure, but a faulty valve. The flight test of the Dragon 2's escape system eventually happened early in 2020. But just as with the Boeing capsule, which was also well behind schedule, the explosion and the inquiry that followed were another unwelcome delay.
2, 1, 0. Ignition.
Around the point of maximum dynamic pressure, the core stage's engines were cut and the escape system triggered automatically. Shortly after, aerodynamic stresses on the tumbling booster caused it to explode.
Cheering in the room, and bright flash there. It looks like maybe Falcon 9 breaking up.
The certification test was a success, and the Dragon 2's next flight will carry astronauts. But there is another spacecraft in development that's worth mentioning. The Sierra Nevada Corporation's Dream Chaser. It's a lifting body craft designed to ride to orbit on an Atlas V, but return to the ground via a commercial landing strip. So far, the Dream Chaser's only flights have been glide tests. As a cargo ship, the Dream Chaser can return a 1,750 kilogram load to the surface. As a crewed vehicle, it is designed to take from 2 to 7 astronauts. The European Space Agency has shown interest in the craft, with the possibility of launching European astronauts atop of French Ariane. The craft will use the bipropellants methane and hydrogen tetroxide for on-orbit maneuvers, doing away with the highly toxic hydrazine. When the space shuttle landed, it had to be at a restricted runway where suited ground staff purged the craft of residual hydrazine. Originally in the running for a NASA contract for ferrying astronauts to the ISS, it missed out because Sierra Nevada could not comply with NASA's 2017 deadline for crewed missions. The favored contractors, Boeing and SpaceX, both failed to meet that same deadline. But the Dream Chaser has a contract for cargo missions to the ISS, and an expendable cargo module known as Shooting Star is being developed. The company still plans a human-rated version of the Dream Chaser, but it's unclear when the craft will fly. Cape Canaveral's Launch Complex 17 was the starting point for many historic Delta II missions. Since the demise of the Space Shuttle, NASA infrastructure from the earliest days of spaceflight has been eliminated. Since the heady days of the space race, NASA's budget has been steadily trending downward, and various launch sites have been given over to the private sector. While NASA has been overseeing the commercial craft that will continue to service the research work carried out on the ISS, its sharpest focus has been on the new Orion spacecraft and the giant space launch system that will boost it to orbit. After its establishment in 1958, the agency's challenge had been to master space technology and then to reach the moon. But since then, the exploration side of NASA's charter has been achieved by robotic missions. Now, a new plan called Artemis will return to the moon. It relies upon the Orion spacecraft and the SLS. The Space Launch System will be the most powerful rocket yet built. And although the design features the latest technologies, most of its components are derived from the Space Shuttle. The Block 1 version, which will send an unmanned Orion spacecraft to orbit the moon, features a central core that owes much to the shuttle's external tank. At the base of the central core are 4 RS-25 engines. The shuttle had 3 of these engines, and NASA still has 16 left over from the shuttle program. Although the engines remain the same, their control systems have been redesigned. Each one has been exhaustively tested, and when the original batch have been utilized, an upgraded version, the RS-25D, will be available. Flanking the central core of the Space Launch System are 2 solid fuel boosters. Again, a refinement of shuttle technology, but with each booster having 5 instead of 4 segments. The new design has been rigorously tested. The boosters will only burn for the first 2 minutes of flight, each consuming 6 tons of propellant every second and providing more than 75% of the rocket's thrust. Unlike the shuttle's boosters, these will not be reusable. The upper stage for the Block 1 configuration of the Space Launch System is called the Interim Cryogenic Propulsion Stage, the ICPS. It's a stopgap modification of the Delta Cryogenic second stage, used with the Delta 3 and 4 launchers. In 2014, a Delta 4 fitted with this upper stage lifted an Orion spacecraft to its first orbital test. The Orion, with a dummy service module, was boosted to a height approaching 5,800 kilometers, allowing it a high-speed return to Earth similar to a lunar mission. The much larger exploration upper stage was to replace the ICPS for the first crewed mission atop a Block 1B launcher, but design changes have led to delays, and the EUS now won't fly till the 4th Orion mission. The Orion spacecraft itself will comfortably accommodate 4 astronauts for 21 days, with the crew breathing air at atmospheric pressure. The craft is intended for missions beyond Earth orbit. It's designed to integrate with larger modular structures such as habitation modules, specialist landing craft, or the planned lunar gateway. Instrumentation and the control interface are primarily via a touchscreen. The digital control enables weight saving through the absence of wires and switches. The Orion Service Module is the European Space Agency's contribution to the craft. It's derived from the automated transfer vehicle which delivered cargo to the ISS. Oxygen and nitrogen cylinders in the service module supply air. There's a water storage tank, and wastewater is not dumped but recycled. A 4-wing solar array generates 11 kilowatts for battery charging and powering the electrical subsystems. For propulsion and maneuvering, the service module is equipped with a version of the same system used by the Space Shuttle. But like so many aspects of this spacecraft, the system can be easily replaced when alternate models under consideration become available. The third important piece of the Orion craft is the launch abort system, mounted above the capsule. 3 different types of solid fuel rocket are designed to fire at the first hint of a malfunction in the launcher.
1. Ignition.
The system was tested in July 2019 above a Minotaur booster, a highly modified peacekeeper missile. Engineers were delighted with its performance. Launch infrastructure is being upgraded for the SLS, and there's increased activity in preparation for the first test of the big new rocket. There were celebrations as the core stage left the Michoud assembly facility. But it hasn't gone to Cape Canaveral, not yet. It was taken by barge to the Stennis test facility in Mississippi, where the stage will be powered up for a series of tests known as the Green Run test campaign. The date, or even the year, for the first launch has been put back a number of times, although it could be as early as 2020. NASA's exploration initiative received a jolt in 2019 when US Vice President Pence, the chairman of the National Space Council, called for NASA's exploration initiative to be accelerated.
It is the stated policy of this administration and the United States of America to return American astronauts to the moon within the next 5 years. And now's come the time for us to make the next giant leap and return American astronauts to the moon, establish a permanent base there, and develop the technologies to take American astronauts to Mars and beyond.
The existing plan had called for a moon landing no earlier than 2028. The month after the Vice President's speech, NASA announced the Artemis program, Artemis being the sister of Apollo. Late in 2019, companies were called to tender for a lunar lander and for a lunar space station known as the Lunar Gateway. The timeline calls for Artemis 1, an uncrewed Orion craft, to enter a series of looping orbits of the moon in 2020. Astronauts are in training for Artemis 2, due to launch in 2022. The current proposal will see a crew of 4 sent to a retrograde orbit of the moon in a flight that could last as long as 21 days. The powerful exploration upper stage will not be ready for this flight, and its proposed trajectory has been modified to accommodate the limited capacity of the interim cryogenic upper stage. During this time, the Artemis plan calls for commercial launch services to make a series of uncrewed flights to position elements of the Lunar Gateway and Lunar Lander in orbit around the moon. A contract has been signed with Maxar Technologies for a power and propulsion element. Some see this phase of the Artemis program as a weak link, because the US Congress has been reluctant to authorize additional funds. There are no concrete blueprints for a lunar lander yet, and some have suggested that the 2024 deadline is being pushed too enthusiastically. Artemis 3 will see a male and a female astronaut land near the lunar South Pole, where ice exists within permanently shaded craters. Long-term goals for NASA's Space Exploration Initiative include the development of technologies that will enable a landing on the surface of Mars. Finally, a different form of spacecraft will soon be taking passengers. Virgin Galactic will start taking paying customers to space in 2020. Everything about the company's spaceships, Enterprise and Unity, is reusable, and Virgin is building 2 additional spacecraft. Passengers will experience weightlessness for about 6 minutes. Virgin is also entering the satellite business with a launcher service using a 747 called Cosmic Girl, acting as an air launch mothership.
Hello, everyone. Here we are again for another one of our live conversations. And these are live conversations. I always am amused when I see in the chat, people say, is this live? Is this live? Yeah, it's live if you're watching it live, right? If you're not watching it live, it's not live. And I don't know, maybe just to establish that fact, it's always good to respond in real time. There was one question here from someone in Fiji. I don't know where the question went, I should say. It had to do with black holes and string theory. If you want to ask that question again, our participant from Fiji, I'll try to look at it. But the main event today, as you all know, is a conversation with Lenny Susskind, who's really one of the great theoretical physicists of our time. So it's an exciting guest to have on the program. As many of you know, Lenny has had profound impact in string theory, black hole physics, quantum mechanics, elementary particle physics. I mean, it's quite a lot of accomplishments. And we'll obviously only be talking about part of those insights, but I think we'll likely skew heavily on black holes. You know, as you reach the end of a year, there's a tendency to think back on the good things, the bad things, summarize, you know, there are all these best of lists, worst of lists, things of that sort. If I was going to focus upon the best of physics, or let's say theoretical physics in 2020, perhaps even earlier, black holes would be near the top, perhaps at the top. You know, we've had a great run and it is continuing onward. And we're going to discuss today some of the puzzles that remain, but some of the deep puzzles of the past that today just are not as puzzling any longer. It's not that everything has been resolved. Right? It's rare that deep puzzles just get fully, thoroughly resolved. But there are many things that were very unclear even as early as 15, 20, 25 years ago that now have really been unraveled. And Lenny and a bunch of other folks that will no doubt make reference to, critical to making that happen. So Lenny will join us at about 1:30 or so. I'll do a little bit of Q&A, maybe just a couple questions if there's something to get us going. And then I'll maybe give a little background to the conversation that we're going to have with Lenny. So here's a question from Captain Viam. How are dark energy and dark matter related? Captain Viam asks. And I like questions like that because the answer is short. Basically, I don't know, and nobody does know how these dark things are related. They may be related, they may not be related. Remember, dark matter is this idea of matter that is out there, we believe, in space. And we come to that conclusion because when we take account of the gravity that can be exerted by the matter that's not dark, which means matter that we can see, gives off light, reflects light, matter of that sort, the amount of gravity that such matter can exert just is not enough to account for the motions that we see through astrophysical measurements, astrophysical data, right? I mean, the analogy that I'd like to use, I think it's a pretty good one. If you have a bicycle wheel that's wet, as it spins, you know that the water droplets fly off as the wheel turns. Similarly, in galaxies that are spinning, if they're spinning at a sufficiently fast rate, stars should be flung outward. And we see galaxies for which the stars should be flung outwards, but they're not, which must mean there's something else out there that's holding those stars inside of those galaxies. The belief is that there's additional matter beyond the matter that we can see with our telescopes, and that dark matter is responsible for the gravitational pull that's keeping those stars from flying outwards like the water droplets. Good, that's dark matter. I should say, there's a lot of dark matter, we think, when you do these calculations. There's on the order of 4 or 5 times as much dark matter as there is ordinary matter, you know, the stuff that we're made of. Dark energy is a different beast. Dark energy, the most convincing evidence for it are these observations that we've discussed in this series from time to time of the accelerated expansion of space. Space is not only getting larger over time. That was a shock, right? That was the shock that initially was really confirmed through the observations of Edwin Hubble. But not only is the universe getting bigger, it's getting bigger at an accelerated clip. So the expansion is speeding up. How can expansion speed up, right? Galaxies, they pull on each other with the force of gravity. Force of gravity we usually think of as pulling things inward, but yet something's pushing outward. And the remarkable thing is that in Albert Einstein's general theory of relativity, gravity can actually be repulsive. It can push outward. Not if the source of that gravity is a clump like a star, a clump like a galaxy, a clump like a planet. Rather, if there's a diffuse energy that is spread uniformly throughout a region of space, then under modest assumptions, it will give rise to a repulsive push, an outward push that can drive the expansion of space to accelerate. And because this energy does not itself give off light, we call it dark energy. So there are the two dark things, dark matter, dark energy. And again, I gave you the amount of dark matter. Dark energies, in terms of the energy mass budget of the universe, is even more substantial. On the order of 70% of the mass energy of the universe is this dark energy. So that are these two components. Now, are they related? Many people have written down theories which suggest that they are. None of these have really gained the consensus of the scientific community as yet, but who knows? You know, they both have dark in their name. Is that the end of the connection, or is it deeper? I don't know. All right, anyway, so that's a good question to get us going here. Mark Kennedy also asks, how much do you miss Mama Joy's? I don't know what that means, but it does ring a bell. Somewhere deep in my childhood or something, I know what you're talking about, Mark, I think, or maybe not. Maybe it's something that I don't want to remember. I don't know. But anyway, I can't answer the question because I don't remember exactly what it means. A quick one more before we head on to a little bit of background. Physics Forever asks, what are strings made of? We'll talk a little bit about string theory here today, no doubt. Lenny Susskind, founding father, pioneer of string theory. I'm sure it will come up in our conversation. And look, when you think about any proposal for what stuff is made of, and you think back on the history of ideas, any proposal for what stuff is made of seemed to ultimately have finer stuff inside of it, right? Molecules made of atoms, a nucleus with electrons in these fuzzy quantum orbits. The nucleus has smaller things, protons and neutrons. Inside protons and neutrons, smaller things called quarks. If string theory is right, big F, really. We'll talk about that. Then inside of these particles are these little vibrating filaments, these string-like filaments of energy. So if that's the correct picture, a natural question is at the end of the line, have we reached the smallest of the Matryoshka dolls? If I'm pronouncing that correctly, no doubt somebody will correct me. You know, the Russian dolls, each has a smaller doll inside of it. Is it that strings have some smaller entity inside of them too? I don't know. Could be strings are the end of the line. Could be that there are finer ingredients. In some sense, string theory even suggests that possibility with things called D0 particles at some level. Maybe we'll talk about that a little bit too. But it's a natural question and one that we don't fully know the answer to. So that's two questions that we don't know the answer to. Maybe there's a question here that I can actually answer. That would be nice. Give me a little boost to keep on going. Yeah, another question about string theory. Let me just find Tishya Patel. Can we describe the fabric of space-time as made of particles? I seem to be drawn to the questions that I can't answer here this afternoon. And in a sense, yes. So in the quantum mechanical framework, the forces that influence how things move, the electromagnetic force, the nuclear forces, they're all part of the standard model of particle physics, which envisions that those forces are indeed communicated by a particle, right? For the electromagnetic force, photons, nuclear forces, W and Z bosons, and so forth. Now, gravity is a force of nature as well. Einstein tells us that gravity is associated with space-time. The geometrical structure of space-time determines the gravitational influence that a body moving through that region of space-time will experience. Now, if you believe, as most of us do, that quantum mechanics and general relativity have got to come together, then the paradigm of a force being communicated by a particle will spill over to the gravitational influence as well, and that gives rise to this notion of gravitons. No one has ever seen a graviton. We're not surprised by that. It's the smallest packet of the weakest of nature's forces, so it's not as though we have expected to see it lighting up our detectors, and it hasn't, so not a mystery. But if this idea is true, then you can actually think of the fabric of space, which is the medium of gravity, as being a whole huge collection of gravitons that are arranged in a coherent pattern that manifests on large scales as the geometry of space-time, but on small scales would have this distinct particulate quantum mechanical description. So I can't say the answer is absolutely yes, but certainly there is a natural intellectual pathway that would take us to that picture. All right, good. Let's, I'm happy to, again, answer questions as they come through. And as in the conversation with Lenny, I'll try to look. Sometimes it's hard. Some of you have asked why, for instance, in the conversation with Roger Penrose that we had last week, why I didn't turn to some of the questions that you ask. And honestly, I just get so carried away in the conversation sometimes with the person I'm speaking with that breaking away to try to scan through the list of questions can be difficult. We do have somebody looking at those questions right now. So if you ask something that's really on point, highly relevant to where